freeze when the temperature gets below freezing, right? It's like, just like water, similar to water. And that would mean like the pipes in your house, the pipes would crack. So in order to keep the spacecraft safe for a long mission, you have to apply heater power. This fuel does not do that. It goes into what's called the glass transition phase. So when it gets really cold, it just gets hard. And then when it warms up again, it comes out. And we've done some studies, especially we were looking at some Mars South Pole missions, where you could put a lander down there and do some hops in the spring and look at geysers coming out. What's nice about that is during the winter, you could let the fuel go into glass transition, and you could save that additional power for science and payloads throughout. So for an exploration perspective, I think that's one of the many facets of this propellant that I like. So.
And I'm going to pick up on something Chris talked about. One of the things that we're most interested in is at Aerojet Rocketdyne, we've seen a real trend coming on in the exploitation of these CubeSats and small sats for a whole variety of missions. And up until now, typically those haven't been able to have propulsion. And this is going to enable that to happen. So one of the things that we see is that added performance that Chris referred to is really good for these kinds of spacecraft. You're volume limited, you're pretty small, and this gives you the ability to do some pretty cool stuff in maneuvering around in Earth orbit, possibly going out to the moon, possibly even to Mars. So this is really tying in nicely with NASA's mission, and as well, a lot of commercial people are interested in this. And as Chris said, they're not used to dealing with the hydrazine fueling and things like that. These are non-traditional guys that are building these in, sometimes like in a workshop that's almost like in an office park somewhere. So they like to be able to do this with this non-toxic fuel. The other thing that I'll say is, in addition to the markets that we're seeing, it also opens up just a whole new range of missions that you can do with having the ability to use these small spacecraft. And we're very excited about that at Aerojet Rocketdyne as well.
All right. I'd like to just look at the spacecraft model that we have here. This is a 1/3 scale model of the GPIM spacecraft. The back end here is the Ball BCP-100 bus. This is the third configuration of this bus that we have flown. This spacecraft bus, was built in 46 days and acceptance tested, so we have a very mature process here. We're actually wrapping this technology around a couple of other NASA missions right now. Same component, slightly different form factor. The upper deck here is the propulsion payload, the non-toxic AFM-315 payload. You can see 5 of the rocket engines on here that Aerojet provided, and we built and designed this subsystem together. So, overall, it's a very compact, very robust system with a lot of demonstration. We've done a lot of work to make sure this was going to perform successfully on orbit and the fueling. We also, as I mentioned earlier, we were able to put on here some additional payloads. So what's wrapped around here and not shown for clarity what the prop subsystem is an integrated MLI, a NASA SBIR technology that I got to fly for free. And we put on 3 Air Force avionics packages late in the mission to get them some additional data too. So.
Yeah, so just to maybe kind of wrap up, Chris mentioned there's 5 of these 1 Newton thrusters on board here. We're going to put them through a whole series of tests on orbit over about 13 months. They'll do maneuvers where they actually move the spacecraft. We'll do maneuvers where they turn the spacecraft. We'll fire them in short pulses. It's going to give us a really good validation on orbit, and that's what's critical about this, because we see these missions out there wanting to fly this, but nobody wants to be the first. They always want to be the second person after it's been demonstrated in space. So we're really thankful at Aerojet Rocketdyne to be part of this mission with Ball and with NASA. We appreciate the NASA STMD giving us the chance to do this in space. And the last thing I'll mention is just what Chris said earlier about the idea that you can actually FedEx this stuff. So we're looking at combining some of our expertise in in-space propulsion, where we've been the leaders for years and years. We've made almost 20,000 of these little hydrazine thrusters. In the future, if that starts to change, we want to be the guys that make the green propellant thrusters. And the other cool thing is we're finding ways we can use additive manufacturing, which is one of our other key technologies we're working on. And we can actually make these little modular propulsion systems maybe and just ship them to the CubeSat guys, and they can bolt the propulsion system on right at the launch site, and that's all they got to do for integration, which is a big savings, as Chris said.
So, are we ready for some questions?
Sure.
Over here, third row, if we can get the microphone this way.
Yes. What was the breakthrough in the composition of the fuel that reduced the levels of toxicity? I'm just interested into what it's actually made of.
Well, the actual chemistry is somewhat proprietary, but what I will say is it is a chemistry composition. If you look at hydrazine as an example, you put it on a bench top that has very low vapor pressure, which means it starts evolving hydrazine into the room that you're with at the same time and reacts with everything. This fuel does not have any vapor pressure, but you have it on a beaker on your desk in front of you, you can't smell it, it can sit there. And when we looked at some of the safety issues, there's a burn barrel test for DOT. This stuff has a very high reaction temperature. The engines have to be hot before we use it. When we did the burn barrel test and the container broke, it put the fire out, which is, so you can, there's other safety issues we haven't really got into here, which we can talk about some other time, but yeah, it's very safe to handle. It's almost impossible to detonate this stuff, which with hydrazine or any other hydraulics, you can do that readily. It's a very, very stable fuel.
Is there anything organic in it, or is it all chemical?
No, well, it's all chemical.
Yeah.
But I mean, it is green. It has a very low toxicity, but it is an explosive. I mean, it is a rocket fuel, right? Very high performance. But, yeah.
Okay, I think we have another question over here from.
So I know that this is the first test for it, but how long do you anticipate before this actually is in practical use?
Sure. Well, I think both Chris has seen it, Ball, and we've seen a lot of interest for this kind of fuel. As I say, there's this whole burgeoning market of these small satellites out there. So we think as soon as we get the demonstration flight in and we start seeing the data come down from GPIM, we're anticipating we'll start getting orders pretty quick.
All right, let's thank Chris and Joe. We've now heard about the two technology demonstrations, and we'll move on to the science. So NASA's spacecraft are under constant attack, not by aliens, but by our own sun. Outer space is a very harsh environment. So what's hot in radiation research? Let's welcome Dr. Nikki Fox, Director of Heliophysics Division at Goddard Space Flight Center.
Thank you. Good afternoon. It is a pleasure to be here with you today. And so I'm Dr. Nikki Fox, and I have the world's best job because I get to lead NASA's Heliophysics Division at NASA headquarters. And so it's a very, very vibrant, very exciting time to be a heliophysicist as we continue to launch more and more missions. And so we're very excited to be launching new ones with this big launch tomorrow. So if I can direct your attention to, I like to call it my baby picture. It's everything that we have in the Helio fleet right now. And so you see Parker Solar Probe launched last year up there studying the sun's corona and giving us the data we've waited so long to actually be able to explain the dynamics of our sun. But obviously we have all of these very, very key assets that are in just the right locations. And I know it looks like it's really busy up there. Remember, space is really big, so there's a big space between all of those missions. But we go all the way from the Corona and then our Voyager spacecraft having crossed the heliopause recently. So they all have this key role in being able to explain what is going on the sun and how that impacts us here on Earth. And so we're always excited to welcome new members to our family. And of course, with this mission, 24 payloads, they're bringing an awful lot of friends with them. But we have two science payloads that are on this mission. They are really looking at the effects of space weather. And so of course, space weather, meaning things that are driven by the sun, carried towards our planet through the solar wind, and then causing impacts to technology here on Earth. And the more and more we start to rely on technology every day, the more we become susceptible to these big space weather events. Space weather has many different kind of flavors. So today I'm going to focus on one area in particular, which is the Van Allen radiation belts. Of course, the first discovery of the space age, when we realized space wasn't empty, but it was actually a really, really cool place to go and explore. So if we can run the video, you can see just how dynamic these Van Allen radiation belts are. There are two of them, an inner belt, mostly protons, but actually very dynamic. We didn't realize until we had the Van Allen probe mission that has been up there for 6.5 years, really telling us all about the dynamics. And you can just see this huge amount of particles that are going all over the place. The radiation belts themselves can pump up and get very big. They can get very, very dense radiation, very, very high energy particles. And because the radiation belts are kind of continually moving, it's almost like they're breathing in and out. There are spacecraft that often are not meant to be in the radiation belts that suddenly find themselves engulfed by the radiation. And so those components that are on those spacecraft can be extremely susceptible to these space weather events. As you can see from this poor little spacecraft, who's going to be quite upset in a minute, as it gets hit with radiation, and then unfortunately lots of nasty things happen to those components, and the poor little thing falls over. And it's a very sad little spacecraft. If only it had had an atomic clock, it might have been able to right itself, but it didn't. So the poor spacecraft is crippled. And what we are doing with this experiment, we are kind of stowing away on another spacecraft, the Air Force Demonstration Space Experiment, DSX, and we are a little stowaway payload. And we have 4 technology experiments on there. They're looking at, one of them is looking particularly at cosmic rays, so all the nasty guys that come from outside our solar system, kind of where Voyager is right now, and coming in and impacting us here. We have one that is looking at what is the right dosimeter, so what something that's going to measure the total dose, how much radiation we're seeing, which is the best one. Let's fly a whole bunch of different ones that you fly every day in space technology and look at which one survives the best. We're also looking at a payload that has, it's basically looking at the continual effect of seeing radiation just accruing over a year. And then we have one that it's just taking very simple technologies and putting them next to one another, comparing them, and seeing which one really functions the best. It also helps us to be able to minimize design margins. As you can imagine, mass into space costs dollars. And so if you can minimize the mass that you're putting into space, you can actually save yourself some money. Why launch a battleship if a canoe would do? And so we want to really sort of shrink those margins and get the most we can get from our science. The second payload that is going up are 2 small CubeSats. And if we can run the ionosphere model for me. Oh, actually, I'm sorry, there's a quick shot of DSX. I didn't run this one, but there is DSX, and so that is the Air Force spacecraft, and we have these 4 little payloads that are stowing away. You can kind of see the box there on the edge, and that is Solar Environment Test Beds, SET. And then if we run the next video, you can see some of the impacts a little closer to the Earth. So we talked about space weather. But there's a very interesting region where space weather from above mixes with terrestrial weather from below. And in this region, you can often get irregularities. We like to call them bubbles, because they literally look like little bubbles in this region. And it can really disrupt communications going from spacecraft down to the Earth. And so we want to make sure we're looking at that space weather too. And so we're launching 2 small CubeSats. My colleague Rick Doe is going to come up in a moment and tell you all about the design of these CubeSats and just what their purpose in our fleet is. And so again, with the heliophysics, we look at what is happening on the sun, we track those events as they come through the solar wind, and we look at how they impact our planet. Having this really nice technology payload, the SET payload, is now kind of doing that final piece of the puzzle. It is not only looking at the sun and how it's affecting us here on Earth, but it's actually now looking at how it's affecting the technology too. So we're extremely, extremely excited to be welcoming the new missions up into our Helio portfolio. And as always, it's a great time to be a heliophysicist. Thank you.
Any questions? Always gets me excited about radiation. Did you have something from, okay, up here?
Hi, yeah, we have a question from social media. How can the space environment test beds help improve future spacecraft design?
That's a great question. So how can we better future design, really because we are taking little components that normally are used in everyday design of spacecraft and looking at how they respond to intense radiation. And so this is very important also as we start to continue our journey back to the moon and then to Mars and beyond. We want to be able to make sure we can mitigate those impacts. And so if you do see the sparks and you see the single event upsets, can we actually correct for those? This is allowing us to really test our ability to mitigate those effects. And obviously, if you're on your way to a far away land, you really want to make sure that your technology can recover and can continue to work, because space weather is going to be a very, very big impact on our Artemis mission, and so that's why we're excited to be getting yet more data to be able to improve our ability to go to the moon and beyond.
Okay, anyone else? Oh, we have a high school science teacher.
Oh dear, it's going to be a hard question.
No, not really. Are you strictly going to be studying the effects of radiation on electronics, or or is this going to have applications for like humans when they get beyond the belts?
So with the SET itself, we're really looking at the impact on technology. One of the reasons we're so happy to be stowing away on DSX is that is a full radiation belt monitoring spacecraft. And so they have space weather instruments on there. And so it gives us the ability to measure the environment with DSX. Of course, the Van Allen probes are still up there providing really exciting information about the environment. Using the entire fleet, we look at what's coming towards us, what's driving those events, and then it's sort of that final piece with SET of what's happening to the technology. The impacts, of course, to humans are that we'll be carrying those type of components on all of the missions as we journey outwards. So really understanding that does have a big benefit to us.
Okay, we have time for another. Anyone? All right, let's thank Dr. Fox. So she gave us a little hint of what's up next. Have you ever been on your way to work in the morning listening to your regular radio station and suddenly you're getting a lot of static? It can be very annoying. But now imagine you're a pilot trying to use GPS to land in inclement weather. Or you're trying to communicate with a satellite and you're getting some similar interference. What's going on in the air up there and what can we do about it? With more on the Enhanced Tandem Beacon Experiment, let's welcome Rick Doe, Payload Program Manager with SRI International.
I'd like to thank NASA and the Air Force for giving us a chance to pull off this mission. The Tandem Beacon Explorer is a CubeSat-based heliophysics mission to investigate naturally occurring disturbances in the upper atmosphere. Our objective is to understand when these disturbances that Dr. Fox has referred to as bubbles will occur so that we can better forecast them and obviously take actions to mitigate them. So as far as background is, I should talk a little bit about the ionosphere. When the sun's rays hits the upper atmosphere, there's a fraction of those neutral atoms and molecules that are ionized. And that's what we mean when we say the ionosphere. And that is the collection of suspended plasma that affects radios traveling from the space to the Earth. And so those long radio waves, which are essentially light waves, are slowed down or sped up by going through changes in density in the ionosphere. And they're particularly sensitive to sharp gradients. Well, a sharp gradient is right where a bubble forms. So we're very, very interested in finding out what are the driving forces behind these bubbles. And my colleague, the PI, Dr. Roland Sonoda at SRI, has noticed, as have others, that there is a preponderance of bubbles that form over large tropospheric weather systems like hurricanes and large weather systems, weather. And so we have an instance where space weather is being driven from forcing from above as well as forcing from below. And that runs counter to a lot of what we think about. So why should I care? Again, we've heard that navigation is an important theme in traveling to space, and it's obviously an important theme in traveling to the coffee shop. And for us on Earth, we would like to understand, can things like commercial aircraft auto-navigate? And so the FAA has encouraged people to use GPS signals as an aid to other navigation tools for the pilots to get you safely to your destination. If we can know that GPS will occasionally become unreliable, then that informs a safety issue. So it's important to us. And I think we're going to roll a little bit of video that shows the formation of the bubbles. This is a sort of a normal, undisturbed ionosphere. And then again, from disturbances from below and above, you get one of these low-density bubbles that percolate up. And these, this is a real hindrance. And so basically, we're trying to find out the basic physics behind the forcing from below and above so we can better forecast these ideas. Let me tell you a little bit about our mission implementation. SRI has been building basic science beacon experiments since the mid-1960s. So our payload is a 3-band transmitter that puts out a pristine signal above the disturbances and sometimes within the disturbances that can then be measured for disruptions on the ground. So the ground receivers, we have about a dozen scattered throughout the Pacific regions that will listen for how the amplitude and phase of these radio signals, these pure pristine signals, are distorted. We work very closely with our colleagues at the University Mission Exploration Lab, Dr. Jamie Cutler and his students. In fact, we've been working on this since 2014 when we finally got our optimal ride to low latitudes. And the students worked incredibly hard at trying to make a spacecraft that is basically a flying radio station. And some would say it's an antenna farm. And if we could cue the video, which is the end result of a lot of engineering work that the students put into deploying safely. And there it is. So it's an origami flower. So that's our TBEX mission. Again, we'd like to very much thank NASA for giving us the opportunity to put together this investigation. We'd like to thank the Air Force for the gift of taxpayer-supported kinetic energy to get to space. And I'm open to questions.
No? Thanks, Rick.
Sure.
In fact, let's give all our speakers this morning another round of applause. So if you're looking for more information on any of these missions or any space technology, you can go to nasa.gov. For updates on the rocket launch, you can go to nasa.gov/SpaceX. I'd like to thank our NASA social participants in the room today for being our audience. We hope that you will share some of the space technology and science with your followers, as well as some of the exciting things you're going to see during your tour of Kennedy Space Center. So now, let's go get ready to launch.
right, everybody, that was the little press briefing they gave us. So I'm still streaming, and sorry I didn't get a chance to introduce what I'm doing here to everybody, but hold on just a second. I'm still working on a lot of this technology. I'm getting it worked out for tomorrow because I don't want to be messing with it now. I want to see what's possible with the bandwidth and everything else. So anyway, I will give you more details on what's going to happen tomorrow as we as the day progresses. So anyway, for those of you who just got here, I'm Tony Darnell from DeepAstronomy.space, and I am at the NASA Social event for the next Falcon STP-2 launch that's happening tomorrow night. And I'm at Kennedy Space Center in the press room where we are trying to I guess we're just getting acquainted with everything. We're going to be, today, this event was pretty much it for today. They gave everybody tickets to go to the Space Center, to Kennedy Visitor Center today, which I won't be doing because I don't have time today, but I will, tomorrow will be an all-day streaming event. And I'm going, now that I know what works and what doesn't, I'm going to send more details on my channel on both YouTube, Twitter, and Twitch. So I needed to see what worked. I didn't even know if I was going to have bandwidth or not. So let me know if this audio is okay in the comments. I don't have my chat clients up right now, but I will hopefully have some of that tomorrow, especially on Discord. I'm definitely going to have Discord up. So there's a Discord server for Deep Astronomy. The link should be in the description box of this video, so check it out. A lot of big turnout here, huge amounts of people here at the NASA Social event. So a lot of people. Of course, what's really cool is I'm looking forward to tomorrow the most because I'm going to get to see some tours of things I've never seen before. I've been to the visitor center a million times, but I haven't been to some of the complexes that they have around here. So I'm looking forward to that. I'm going to live stream most of it if I can. If not, then I will at least record it and post some videos after the fact for Tuesday. Yeah, for Tuesday. So here's what I think is going to happen so far. I'm going to have an event set up, a YouTube streaming event on my channel from which I will stream. I won't always be able to be live 24/7 while I'm here. So there'll be times when that stream will be blank. It'll be empty. But there will be and then there'll be times when I'm live. What I'll do is I will put in the live chat when I am going to be back live again. And so there will be times on the stream tomorrow on YouTube now where you won't see anything. It'll just be a blank screen. But then when I go live, it'll come up again, and I will put that on the live chat. That's what I think I'm going to do for tomorrow. I had hoped to set up a system, and it didn't work today, where I remotely control my computer, which has Wirecast on it, so that the times when I'm not live, I am playing some videos. So you always have something to watch, because I didn't want there to be blank screen time. But I can't be on all the time while I'm here. So I'm going to do it this way, and we'll try it out. So where I'll be streaming is YouTube on a event that I'll create tonight, and I will send the link out on all my social media, and it will be live the entire day. It'll be streaming, but sometimes it'll be blank. I can't help that. I'd hope to have something playing during that time where it's blank, but I can't do it. I'm just one guy, and I don't have enough resources. But I will put in the live chat when I'm planning to go live next, and then you can tune in then and see whatever's coming in next. I'll try to live stream as much as my bandwidth and batteries last. It's all going to be battery limited here today. When batteries go dead, I can't do streaming anymore. So, but I'll do it for as long as I can. Should be at least a good couple hours for tomorrow. And then, of course, I'm going to live stream the launch. It's at 11:30 p.m. Eastern Time tomorrow night, so it's a night launch. It won't come, but at least you and I can share it together. I will definitely stream that live. Okay, we're being herded out, so let's go.
Is that eventually?
Maybe it'll be back in 17 or 18. Maybe they tinker with it. Watch out.
Time to adjust. There we are. All right, time to adjust some settings here. So let's go walk around. Oops. So many people taking selfies. That's what you get with NASA social, I guess. But anyway, hopefully I'm still live streaming. And I'm outside now. And let me show you something really cool.
All right, let's go down to the clock, everybody.
Isn't that cool? Right there. That's the NASA Vehicle Assembly Building. It's a bright day today. Bright day.
I live here, I don't mind. I wouldn't be wearing jeans. I thought you had to wear jeans. We do. That's what I thought too. Oh, it's fine. Play shoe raw.
That is the Vehicle Assembly Building right there. Oops. Wide camera shot again. So if you've never had a chance to come here, you got to do it. Oh, we're going to the clock next. Yes. Good. We're walking to the clock. Now let me show you this, because not only is the clock there, the countdown clock, but right behind it is the vehicle or the launch pad. So let me turn this around. There's the countdown clock with the launch pad right behind it. That's the new clock. They finally replaced the old one. The old one is
Yeah. I looked through it. What is going on? Exactly. I looked. I was like, oh, I don't know.
There's a nice launch area right there, launch watching area. I've never used that one. I've never been there. But there is the launch facility in the distance with the clock for STP-2. All right. All right, let me see. This is about the best my zoom does. Oh, it's time for a picture. We're gonna be in the picture, guys, because I'm gonna keep streaming, even though the picture's being taken.
Real friendly.
Where should I stand? I better not stand up front because I've got the camera.
Okay. Yes, sir. Close together.
Please don't have your orange badge in the photo. Thank you.
Come on, get her in, closer. See the lady in the black right here on her knees? She's the center. Okay, all right. Orange badges, cover them up.
Cover the badges.
Hold them up. Cover your orange badges.
I hold them up.
On the end, slide in. Come on, let's go. Okay.
All right.
I messed up.
All right, we got a picture took. All right, so here we are, front and center. I don't know if I like the new clock. I like the old one better. I like the old one better, I think. What do you guys think? All right. Well, I think I'm going to stop. Well, what the hell? We'll keep going. I mean,
yeah, this is where I proposed. So it's kind of like, wow, 8 years ago. 8 years ago, almost to the month. So STS 134 was in April, and then it launched in early May. So still married. Wife let me come to that. I tried to get her in too. I was like, ooh, let's get to be romantic, but now, bye, honey. Enjoy hanging out with the 2-year-old. So yeah, that's why I'm partial to the old clock, because I have the. These are the series of photos that I had of like. It's the same size. It was all just light bulb though. So it's still the same frame, even like the base is still the same. Yeah. So it's hard to see in some of those. There you go. Yeah. She's very surprised. And then the Washington Post, you know, somebody she screamed so loud.
Get on the bus.
all right, guys, I'm going to go ahead and stop the stream. I'll try to pick it back up here in just a little bit. Hopefully this is coming through.
Or what you're wearing.